So I just want to say thanks for having me. This is my first SciPy, and I'm so excited to be here. My name is Erin Arai, and I'm a graduate student in the Mechanical Engineering Department at Boston University. And I work with Professors Emily Ryan and Professor Cheryl Grace simulating multi-phase flows. And in particular, we're interested in how bubble cavitation in fuel injectors affects the longevity and efficiency of these fuel injectors. So why do we study bubbles? We study bubbles because of reasons like this. So this is an image showing pitting damage due to bubble cavitation in a fuel injector. These images down here are X-ray images of a fuel injector before and while it's running. These were done at Argonne National Labs. It's actually an awesome YouTube video. These are just a couple of stills. So you can see that bubbles form throughout the system, and when these bubbles collapse close to a surface, the implosion from their collapse actually is hugely forceful. So this middle image, you can see this is a bubble just as it's collapsing, and there's a jet here forming, and it's about to impinge on the surface it's next to, just to drive home how powerful these bubble collapses can be. This is a study from the 1980s where they imaged the bubble collapsing, and while they imaged that bubble collapsing, they also measured the pressure that was being imparted onto the surface next to the bubble. And you can see that peak is about 100 atmospheres, so these little bubbles they impart large forces. In the case of fuel injectors, it's actually a double-edged sword. So, if bubble cavitation occurs inside of your system, then it can cause damage. But if you can tune your cavitation so it occurs right at the end of your nozzle where you're atomizing your fuel, it can actually make your fuel atomization more efficient. And this is a very recent study that is working on quantifying just how much more efficiency you can gain from cavitation being present at that point. So how to model bubbles? It's actually a little bit hard. This is a video taken by a postdoc at BU, different lab, but you can see this is just bubbles in wavy water. So there's a huge range in scale and in the way they deform and the paths that they take as they rise. So if we're going to model these accurately, we need to make sure that we have some kind of numerical method that is capable of dealing with the dynamic geometries that are inevitably going to be present. They are obviously multi-phase systems, and we're going to have to be careful about our interfacial forces. So we're sort of faced with a choice. This is artificially divided, I admit, but we're sort of looking at a grid-based method or a particle-based method. And based on the things we just talked about absolutely needing to accurately simulate a bubble, those aren't really the strengths of grid-based methods. So the deformations in short amounts of time, that's expensive with a grid-based method. Even meshing up a static complicated geometry can be difficult, so never mind if that geometry is changing now at every time step. And interface identification and evolution can also be difficult and or expensive. So that leads us to these particle-based methods where dynamic geometries are often relatively easy to accommodate, and interface identification is often organic because their particles move as your simulation goes on, and it traces your interface for you. So the method we use is called smooth particle hydrodynamics, and this is a Lagrangian particle method. So your domain is made up of particles that carry your fluid parameters around with you, and they move as your simulation proceeds. And it was developed by two astrophysicists in the late 70s, sort of at the same time, and it's been used with great success since then to model all sorts of different physical systems, but in particular free surface flows and multi-phase systems. This is an example of a free surface flow, so it's an example sort of in the dam break category. So at t = 0, you turn gravity on, and your fluid is allowed to flow, and it interacts with this boundary. And you can see that the shape and evolution of that free surface is very organically accommodated by the method. So how does SPH actually work? There's this great paper by Daniel Price, and he motivates how we can think about the method working by posing this question, which is, how can we compute density from an arbitrary distribution of point mass particles? And there are a few ways that you might think about doing that. You could interpolate your mass to a grid. This inevitably sort of oversamples where you have a lot of mass and undersamples where you have less. You can construct a local sample volume. The problem with this method is that your particles close to the edge of your sample volume are going to have an undue impact on your computation based on whether they fall in or out of your volume. So that leads pretty naturally to the idea of using a weighted sum, and this is what SPH does to compute density. So this is actually how you would see expression for density written in any SPH formulation. And you can see we go over our neighbor particles, mass of our neighbor particle, times some weighting function. And you can imagine that we could figure out what the interactions are between all the particles in the entire domain, but then you have a computationally intractable problem very quickly. So we make sure that we choose a kernel that has compact support. So we have a finite number of neighbors that we need to loop over. This is a representation, a continuous representation of a field variable against our weighting function. And if we discretize that, again, we go over our neighbor particles. Mj over rho j is our volume proxy, our field variable, and our weighting function. And we make sure that we choose our weighting function so that with a little integration by parts, we can transfer operators to the weighting function. So this makes implementation easy. And a final takeaway when you think about this method, if I want to figure out what the force on a particular particle is, all I really need to do is figure out what all the contributing forces are from its neighbor particles and sum them all up. So this makes it very easy to add more physics into your system. You just add another term in your sum. Okay, so the code base that we use as our springboard for our work is called PySPH, and it's an open source cross-platform smooth particle hydrodynamics code. It was and is being developed by Dr. Prabhu Ramachandran, who I think spoke about this project last year at SciPy. And so this, part of what's so great about PySPH, as you'll see, is it's really easy to implement new physics. So this is actually an example, a solid mechanics example. It's the elastic collision of two rings. And it's just one of the many built-in examples that come with this package if you download it and install it. Okay, so what makes PySPH so great? What causes it to stand out to us, and why do we choose it for a basis for our work? Well, it lets you develop in pure Python. Hooray, we all love to develop in pure Python, but as we know, sometimes Python is a little bit slow compared to other languages, especially when we're doing, one of these iterative, or doing this operation over and over and over again. So PySPH lets you have the best of both worlds by, so you write your relevant method, and then there's a code generator that literally plucks out the text of your methods. It goes into a Python template, which at runtime generates a Python file, and this is the file that you would have had to write before if you wanted to get this performance. And then it gets compiled into C, and so your code at runtime is executed as C. And just to drive home how friendly this is, so here's our loop method. It is a method of the equation class, and you can see that over this loop, we go over all the neighbor particles, and here's that mass we talked about again, and our weighting function. So the friendliness and transparency of this code base makes it so that you can read a paper and implement a new term basically just by transcribing what you see in the paper into the relevant methods. So for instance here, I was reading this paper. I decided, I'd like to see what this pressure discretization looks like and how it works. And so I subclass my equation. I overwrite the relevant methods. And that's essentially all I need to do. I even added a couple of fields so that I could keep track of what the contribution due to just this term was. And then I go to sort of my mother class, my application class. This is really where the usage is separated from the construction. And I put my new pressure term in for my old pressure term. So this is safe because there's no chance rather that I've messed up momentum equation viscosity. There's no chance that I've messed up any other part of my simulation. I can really just swap this out and run my simulation again and see. So this makes changes really easy. This is in stark contrast to some of the other available open source SPH codes. For instance, if we wanted to add even just one field to this particular code base, you would have to touch all of these headers in C++ files. You would have to do everything in C++. And so there's a lot of places where you might make a mistake here because you have to change so many files. The user manual for this code base is literally 89 pages long. So it's just not as friendly. It's not as easy for you to get running quickly. Okay, so back to what we would like to use PySPH for. We talked about fuel injectors and bubbles. Fuel injectors are pretty big, complicated systems. So if we want to actually be able to model bubbles in those systems, we better make sure that we can model isolated bubbles first. So there are two sets of cases we're looking at. The first one is bubble shape oscillation. So if you perturb a bubble out of equilibrium, that the surface tension is always going to be trying to minimize itself, right? Which means the bubble is always trying to become spherical. But on the way, especially depending on how you perturb it, on the way, you're likely to have overshoot, oscillation, and depending on how you perturbed it, it's pretty well established the shape oscillations that you should expect to see it go through as it's becoming spherical again. It's some sum of spherical harmonics, which is what you're seeing here. And the other set of verification cases for which there exists quite a lot of experimental data in the literature is the terminal shape of a bubble as it rises through a column of quiescent fluid. So these shapes are governed. This is the experimental data. Those shapes are governed by a few dimensionless parameters. There's the bond number, which tells us about body forces to surface tension, the Morton number, which is a characteristic fluid parameter, and the Reynolds number, which is our inertial to viscous forces. And over here, I've included Hua et al.'s finite volume simulations of these terminal bubble shapes. So it's definitely a verification case that people use. Just a quick overview of how surface tension is often implemented. So surface tension is really a product of the interface between two phases. But now you have a boundary value problem. It's a little bit hard. So in the early 1990s, Brackbill et al. Came up with this continuum surface force method. And the basic idea is I'm going to smear my infinitely small interface out to be some finite volume so that I can apply my interfacial forces as a volume force, which is easier. So basically the way that works is you tag each domain. So here we've tagged our inner domain 1 and outside 0. This is called the color function. And then you smooth that color function out. So you identify some diffuse interface where your actual interface would be. And now that we have this smooth color function, we can compute a color gradient, some interface normals. Finally, we can compute the curvature and then assemble everything into determining what the total surface tension contribution is to your accelerations. Great. So PySPH, of course, already has some surface tension formulations implemented. And that's what you're seeing. That's this video you're seeing here. And this is a one fluid simulation, so you can think of it as being like a membrane. There are no parameter gradients here, but we have imposed surface tension initially in a square region, and then we watch to make sure that it oscillates and circularizes as it should. So this is a good sanity check for your surface tension implementation. And then if we look at some of the pieces that go into that simulation, we see our normals in the x direction are nice and orderly. That's very good. So naively, when I first started using this, I thought, oh great, I'm just going to put a low density area and surround it by high density area and press go, and it's going to work. And of course, my simulation was not very stable, and this is a large density gradient. And if I go and look at the pieces that go into this simulation, I see that I'm definitely having trouble in my normals. And you can imagine what a normal pointing in the wrong direction does for your curvature, especially if your curvature is large. So I realized there were some things I might have to look at. Honestly, I shouldn't have been surprised at all that this didn't work when we think, let's remember how we have been computing density, right? We are summing over our neighbor particles. There's our neighbor particle mass and our weighting function. So if I'm a particle at the interface, my neighbor particle masses are not going to be the same anymore, right? I'm going to have some really big ones and some that are like me. And so one trick is you can pull out this neighbor particle mass and use instead your mass times the sum of your weighting function. Now this is actually how most SPH formulations are already implemented. This was already implemented in SPH or in PySPH. But similar ideas were not. So for instance, there were a few places where we were using mass density instead of number density, and it was equivalent to use number density, and now number density doesn't have a giant gradient. It doesn't know anything about what my particles weigh. So this is one way to stabilize some of these extreme parameter gradients. And I added a couple different pressure and viscous terms because I was curious what the results would look like, and because PySPH is so friendly, it was very easy to do that. Now I put all my sort of modified or additional equations back into my create equations method of my application class. All it goes in, run it again, And I have a simulation that is now much more stable to my density gradient. And you can see this is now a true bubble. I have density 1 in the red, and it's density 1,000 in the blue. And you can see it oscillates and circularizes. And if we look at our normals again, they're much more orderly. So we're happy. It still leads us to wonder, oh, well, maybe there's another way to compute surface tension that has fewer steps, fewer places for us to make mistakes or introduce errors. So there's this paper from last year by Cascading Panchenko, and they generate surface tension in their SPH formulation by pairwise forces. So this is actually much more similar to what's happening in nature. And the idea is particles of like fluids are going to interact more strongly with particles of their fluid than they are with particles of another fluid or a gas, for instance. And so that will generate that net force will be will be generated at your interface, and you can produce surface tension that way. So that work is ongoing. The preliminary results are actually looking good. I don't have any of them here in the slides. But ultimately, this will reduce the number of steps that we need to implement surface tension, and hopefully allow us to have a more robust simulation. And it would be unfair to say that there aren't other surface tension formulations out there. There absolutely are. These just happen to be the two that we have looked at in depth. Okay, the other case that we were curious about, these funny terminal bubble shapes. So this is an image from some work by Michael Manga and Howard Stone from the early 90s, and they were actually curious about how these two bubbles were going to affect each other's trajectories and shapes. We're only looking at the rising shape of one bubble at this point. This is really just proof of possible. So this is more like an oil droplet that you're watching rising here, and there are a number of crufty little things that I haven't sorted out in the simulation. But just to motivate that there's reason to believe that within this infrastructure we should be able to replicate some of these rising bubble shapes. And you can see our Reynolds number isn't completely crazy, and we are reproducing these viscous tails with a qualitative sanity. So one thing I want to mention about simulations like that, we're interested in the transients, the bubble transients. But that means you'd like to make sure that you eliminate any other background transients in your simulation before you put the bubble in. And so, for instance, with a hydrostatic tank, the way I set this tank up is I put liquid in there, and I apply gravity, and I wait for the correct pressure gradient to establish itself. So ideally, you let that happen first before you put your bubble in. And this is just to give you an idea of settling out your environment and then what it would look like to plunk in your bubble after your environment is settled. And of course, PySPH has also, the way it's designed makes this fairly easy for us. So you get to run your simulation in steady state. You run your environment simulation to steady state. You produce a bunch of out files. From those out files, you can inherit the whole simulation state and also information about the solver, et cetera. Get all the particle parameters. Now that gets pulled back into your application class where you have the power to add particle domains, change particle domains. You can adjust the equations that are being solved, and then you restart your simulation. So in summary, I've used PySPH to try to do some preliminary isolated bubble modeling. And PySPH is a fantastic tool, especially if anyone out there is wondering about smooth particle hydrodynamics. You can get this up and running in 10 minutes. You can have those examples like the colliding elastic rings. Probably in 15 minutes, you can have that from install to viewing. So it's hugely friendly. It allows you to work in pure Python, but compiles your code so you still get the benefits of the speed of C. And it's designed to facilitate extension. I really think that it has succeeded in that goal, and I hope that I've convinced you also that it is easy to extend. What I've done, I've made a few adjustments for multi-phase, modified what exists, and included a few additional terms to try and accommodate some more aggressive density ratios. And ongoing are all the bubble cases that I mentioned to you, so implementing this new surface tension, working with restarts to moderate all those little transient things so that we can focus on the transients that we're actually interested in. And ultimately, we'd like to use this new surface tension formulation to continue our submodel work. And that's all I have for you. This is my contact information again. I'd be delighted to continue talking to anyone who is curious about any part of this work. And thank you to the DOE. All my work is funded by the DOE. Any questions?